Video 1, Environmental Science, Fall 2014. These videos will coincide with the readings each week from your textbook, Environmental Science Systems and Solutions, 5th edition. There'll be 1 or 2 or 3 or 4 videos per chapter. And that way the material will be broken up into content versus book chapter size. So what is environmental science? We think of environmental science as an interdisciplinary field. It combines knowledge from different fields within it, such as biology, chemistry, geology, physics, all the other sciences, and even the social sciences. It's very helpful also to have a background in overlapping disciplines such as politics, ethics, economics, and others in order to better understand societal components of environmental problems and solutions. We can break the environment or categorize the environment into 4 spheres. The lithosphere, litho meaning rock, hydrosphere, which encompasses the water cycle, oceans, atmospheric water, etc. The atmosphere, which encompasses gas and also interacts very strongly with the water or hydrosphere. And the biosphere, which comprises all of living matter. Now, matter cycles and energy through these spheres, and they all interact to some level or another, depending on how well they're integrated. People have a major impact on these spheres, especially on matter and energy cycles. The book is set up to talk about the environment as a systems approach. A system is a set of components functioning together as a whole. They're usually hierarchical, composed of smaller sets of systems with even smaller interacting parts. The Earth itself is made up of these larger systems or spheres that have energy from the sun moving through them. When talking or thinking about environmental problems or science, we have the benefit of years of experience that leads to general knowledge or wisdom. This experience shows that short-term emergency actions have been less effective and more expensive than long-term solutions. It also shows that holistic approaches offer the best chance for solving long-term environmental problems. In addition, input reduction solutions, or conservation, conserves resources and both reduce pollution and environmental degradation. According to the throughput model of the environment is a source and a sink for the matter and energy that flow through society. Population and consumption accelerate the flow, leading to resource depletion and pollution, while input of material and energy through the society is called throughput. Environmental resources are sources of throughput, and reservoirs that receive throughput are called sinks. And depending on how throughput works, that sink can either be a sustainable sink or one that leads to resource deprivation and pollution. So let's talk about the environment as a system. A system is a set of components functioning together as a whole. Most systems are hierarchical, composed of smaller systems that are made of smaller interacting parts, like I said before. The global environment can be analyzed in terms of 3 key system traits that all of them have to some degree or another. They include openness, integration, and complexity. Openness refers to the degree of isolation of a system. The Earth itself is open to energy with flows in and out of it in the form of radiation. The Earth essentially is a closed to matter, which cycles over and over again through the 4 spheres. In other words, new rock material or new water material or new gases are not coming in and out of the Earth. So it's a closed system in those matters, but energy is passing through it, so it's open to energy. Integration refers to the strength of interactions among the parts of the system. The degree of integration of global environment is under debate. Most likely the Earth is moderately integrated. The global environment is moderately integrated but highly complex. This complexity makes the effects of disturbance hard to predict. Hardin's first law of ecology states we can never merely do one thing, which means we can't do one thing without affecting the other. The study of complex systems represents a new approach to science that investigates how relationships between parts give rise to the collective behaviors of a system, and how the system interacts and forms relationships with its environment. This is all modeled by equations that try and grasp these complex systems, and they're developed generally derived from statistical physics, information theory, and nonlinear dynamics, which are beyond the scope of this class. But they represent organized but unpredictable behaviors of natural systems that are considered fundamentally complex. Examples of complexity include climate change, ozone depletion and surface ozone pollution, ocean acidification, conservation biology and habitat loss, and acid rain as described in the text. It's not always easy to determine what comprises the environmental system or what affects it. For that matter, what has an impact and what can be measured. Loose integration of complex environmental systems leads to lag times or delays before effects are seen. Systems and chaos theories attempt to explain and quantify the openness, complexity, and integration in a system. Systems theory focuses on regulatory influences or on undefined systems. For example, what actions turn down or minimize changes, as in negative feedback, and what actions amplify changes, as in positive feedback. Chaos theory mathematically models and defines a system so that small changes can be traced to predict effects within the system. Chaotic systems are by definition easily influenced by small changes or actions. Predictions are often difficult or impossible to predict using chaos theory due to multiple inputs or influences. The most famous of these chaos theories is the so-called butterfly effect, where the beating of a butterfly's wing affects winds a continent away. This book focuses on systems theory. Society accelerates the cycling of matter through the four spheres that we talked about, depleting resources and causing pollution. Depletion occurs when the cycling removes matter and energy faster than the natural processes are renewing them. In systems theory, we can have both positive and negative feedback loops. Positive feedback occurs when a part of the system responds to change in a way that magnifies the initial change. An example is increased global temperatures causing further increase by melting some of the glaciers and snow that reflects sunlight back to space. Let me repeat that. An increase in global temperature causing further increase by melting some of the glaciers and snow that reflects sunlight back into space. This results in more surface area absorbing instead of reflecting heat. This is called the albedo effect. It's a term to use to measure how much radiant energy an object diffusely reflects back versus absorbs. Changes in albedo increase energy absorption and therefore global warming. To simplify, think about it this way. Ice and snow reflect sunlight back out into the atmosphere and then into space. Once the ice and snow are gone, Earth, or water, will absorb that sunlight energy and then turn it back into, and then transform it into, transform it back into heat, which then increases global warming. So the less ice you have, the more warming you get. And the more warming you get, the less ice you have. Negative feedback occurs when part of the system mitigates the initial change. So a negative feedback tends to resist a current course of change. For example, when you turn the thermostat down in your home, this causes the heat to come on less and less, and for the temperature to become cooler. And vice versa, turning up the thermostat increases the heat in the house. The thermostat is a negative feedback because the house goes out of equilibrium or cools off, and when that happens, the feedback from the thermostat initiates the system to bring it back into equilibrium. This is happening in the human body as well to maintain temperature in warm-blooded animals. So this concept of homeostasis in the body is a negative feedback loop, always maintaining equilibrium. Another example is the predator-prey relationship, where too much prey in a system results in more predators, and too many predators results in too few prey animals. This system always has negative pressure to go back to equilibrium, and therefore is a negative feedback loop. From this first part of Chapter 1, you should be able to discuss or answer the following review questions. You should be able to define what environmental science is, what the throughput model and a systems approach is as applied to environmental science. What are the 3 key traits of an environmental system? What is the difference between depletion and pollution? You should also be able to give an example of a positive and a negative feedback loop.